Okay, we are going to take a look at exercise 1 on page 75 of your workbook. And let's start by reading this problem together just to get a feel for what they're asking us. Okay, so we've got, and actually I want to make one change to this problem before we do it. Okay, so before we read it, I'd like to get rid of that part of the problem just to make it a little bit easier to do. Keep this in mind though when if you look at my written solutions, they're going to be a little bit different to this problem because of the fact that we just made this change. Okay, so that said, let's see what this is asking us. So a metal can manufacturer needs to build cylindrical cans with a volume of 300 cubic centimeters. The material for the side of the can costs 0.03 cents, and that's 3/100ths of a cent per square centimeter. And the material for the bottom and the top of the can costs twice that much, 6/600ths of a cent per square centimeter. And they'd like us to know what is the cost of the least expensive can that can be built. Okay, so you can imagine that this is the kind of question that maybe a soup manufacturer might be interested in. They know how much volume they want in their can, 300 cubic centimeters of soup, and they know what the construction costs are, and they just like to know out of all the different sizes and shapes that they could build their can, it could be tall and skinny or short and fat, what would the best way to do that be so that they get the minimum cost? That's the problem that we're trying to solve here. All right, so let's maybe start with a picture. We've got a cylindrical can. Okay, so it's going to kind of look like this. And what we don't know, what we're trying to figure out, are a couple of things. What would the radius of that can have to be? So let's label that R. And what would the height be? Let's label that H. Okay, well, we're going to start this problem the same way that we've been starting problems in this section. Okay, by asking ourselves, what do we know in this problem? Okay, well, probably the biggest piece of information is the volume of the can. Okay, this 300 cubic centimeters. Okay, but to proceed with that piece of information, we need to think back to geometry a minute here. What is the formula for the volume of a cylinder? Okay, well, I made us a little bit of a little cheat sheet up here at the top of the page, some formulas about cylinders. And these are not formulas I would expect you to have memorized. These are things that you could either look up or that I would give you in a situation where you needed them. Okay, so the formula for the volume of a cylinder is actually pi r squared h. And so what we know then is that that volume, pi r squared h, has to equal the 300 cubic centimeters that they gave us. That's what we know. Okay, and I'm going to remind you that that's just the volume of the can. And what we're trying to find is the minimum cost here. Okay, we'll give it a name and we'll call it C in this case. All right, well, if we want to minimize the cost, we need a formula for the cost function. Okay, and that's the part of this problem that's more challenging than some of the ones that we've done this far, up to this point. How do we find a formula for the cost of the can? Okay, well, let's see if we can think through this step by step here. Okay, so the cost, I'd like to break the cost function up into two pieces because of the fact that we've got different material costs depending on which part of the can that we're talking about. So we'll break it up into the cost of the top and the bottom of the can plus the cost of the outside of the can. That's kind of a natural way to break it up because the cost of the materials for those different parts of the can are different. Okay, so if we focus just on the first part of this, the cost of the top and the bottom, we could ask ourselves, what's the cost of the material for the top and the bottom? Well, they told us that the cost of the top and the bottom was 0.06 cents per square centimeter. But that 0.06 is a cost per unit area, so we need to multiply that by the area of the top and the bottom. Okay, to turn it into a cost. Okay, and similarly, for the cost of the outside of the can, they told us that that's 0.03 cents per square centimeter. Okay, so we need to multiply that by the area of the outside of the can. Okay, so to proceed here, we need to ask ourselves, what would the area of the top and the bottom of the can be? Okay, well, let's look at our picture. So what shape do you see when you look at the top of the can? I see a circle there. Oh, my can disappeared. Hang on a second here. Let's redraw that. Okay. So the top of the can has the shape of a circle, and the area of a circle seems to me as pi r squared. We've actually got two circles, one for the top and the bottom, so that combined area is actually going to be 2 pi r squared. That's going to get multiplied by this 0.06 that was in front. Okay, so that takes care of the first term here. All right, and then we need to move over and take 0.03 and multiply it by the area of the outside of the can. Okay, well, here's where we need to maybe go back to our cheat sheet up here at the top. The area of the outside of the can, of a cylinder, is given by 2 pi RH. Okay, that's another formula from geometry that we're going to use. Okay, so we have a complete formula for the cost, and then we'd ask ourselves, what's the next step if we want to find the minimum value of the cost? Okay, well, we need to think about critical points here, and we run into the same issue that we've run into a few times. We have a function that has two variables in it, r and h. We need to get rid of one of those variables in order to be able to take the derivative of this. Okay, so we'll do what we've done a couple of times. We'll go back to our given piece of information, the pi r squared h equals 300, and we'll just solve that for one of the variables. Okay, which variable do you think would be easiest to solve for here? Okay, it looks to me like h would be the easier one to get by itself since it's to the first power, so let's just divide both sides by pi r squared. That's going to give us h equals 300 over pi r squared. All right, and we'll take that and we'll substitute it into our cost function everywhere that we see an h. Okay, we can maybe do a little algebra at the same time. So 0.06 times 2, that's 0.12. And let's see, 0.03 times 2, that's 0.06. And h, we just calculated above to be 300 over pi r squared. Okay, I'm going to scroll us up a little bit because I think we don't need those cheat sheet formulas anymore at the top. Okay, and we've managed to take our cost function and to reduce it down to a function of one variable. So in theory, we can take the derivative of this, but the form of our equation is still pretty ugly. This would not be an easy derivative to take. So let's think about, can we simplify this expression? Okay, notice that some things cancel. For example, the pi's cancel. And then we've got an r in the numerator and an r squared in the denominator. We can cancel those. That's going to leave one r in the denominator. Okay, so rewriting this, we've got 0.06, the pi and the r in the numerator are gone, times 300, and then we've got an over r. Okay, and we can do one more thing that'll make this a little bit easier. Well, actually, two more things. We can take 0.06 and multiply it by 300. That's actually going to give us 18, if you do that on your calculator. And then dividing by r is the same as multiplying by r to the minus 1. That's a way of getting rid of that fraction. All right, so we'll take the 0.06 times 300, that's going to give us an 18, and we'll move the r into the numerator and make it an r to the minus 1. Okay, that's going to be an easier derivative to take. Okay, so we are ready then to find our critical points, which means we're going to take the derivative of c. Okay, and let's see, we're starting with the 0.12 pi r squared term, so its derivative, we're going to just use the power rule on that, bring the 2 down, that's going to give us a 0.24 pi r. Okay, and then for the 18r to the negative 1, bring the negative 1 down, and we're going to get negative 18r to the negative 2. We need to set that equal to 0. Okay, so we need to solve that equation, and let's see, what could we do to solve this? We've got some choices. So we can maybe start by adding the 18r to the negative 2 to the other side of the equation. Okay, and because this is an equation that we're solving, it's probably more convenient to rewrite things that have negative exponents in it. So we could maybe go one more step here. Rewrite that 18r to the negative 2 as 18 over r squared. Okay, and now, to get rid of the fraction, let's just multiply both sides by r squared. Okay, notice that if we do that, the r squareds cancel over there on the right-hand side. And on the left, r squared times r is going to give us r cubed, so we'll get 0.24 pi r cubed. And over on the right, we've just got 18. Okay, and sorry to keep scrolling on you here, but I just keep needing more space. This is a long problem. Okay, so we need to solve for r here. So we'll take 18 and divide it by 0.24 pi. Okay, and how do you solve for r in a situation like this? Okay, well, we've got an r cubed, so we really need to take the cube root of both sides. So if we do that, we're going to get r equals the cube root of this entire fraction, 18 over 0.24 pi. Okay, and that is really a job for your calculator. Okay, so if you punch that into your calculator, it's going to give you 2.88 if we round it off. Okay, what would the units on that number be? Well, r is representing a radius, which is a length, and length in this problem was given in centimeters, so that should really be a value in centimeters. Okay, that appears to be our one and only one critical point. Okay, so what did they ask us for in the problem? What were we trying to find? Okay, well, if you look way back at the beginning, they wanted the minimum cost of the can. This is our one and only critical point, so this should be the place where the minimum cost occurs if we've done our work right. Okay, so we need to take that value of r and plug it into our cost function to figure out what the minimum cost is. That's going to be the last step here. Okay, so the minimum cost is going to be c of that 2.88. But we need to remind ourselves of what the minimum cost function is. Here we're going to need to scroll back up again for a minute. Okay, and our cost function kind of started here, and we developed it piece by piece and arrived at a final formula that looked like this for the cost. Okay, so that's what we're going to substitute the 2.8 into. So we're going to get 0.12 pi times that 2.88 squared plus 18 times 2.88 to the minus 1. Okay, and that again is a job for your calculator. Okay, you can substitute that in and go through all the arithmetic. That's going to work out to be about 9.38, just depending on how you round. And again, we could ask the question, what are the units on that answer that we got? Okay, well, you can go back to the beginning of the problem and confirm that cost was measured in cents. And so our construction cost is 9.38 cents. And that's our answer to the question. Okay, and we are done.